Hello students, we will start today's session with discussions on structure of atom. This is given in Unit 2 Part 1 of Chemistry for Class 11. As you know, we are covering the entire discussions based on NCERT syllabus, which is rationalized for the year 2023-24. The existence of atom has been proposed since the time of early Indian and Greek philosophers, who were of the view that atoms are the fundamental building blocks of matter. These earlier ideas were mere speculations, and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by the scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British schoolteacher in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle. As discussed in Unit 1, Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportions very successfully. However, it failed to explain the results of many experiments like it was known that substances like glass or ebonite when rubbed with silk or fur get electrically charged. In this unit, we start with experimental observations made by scientists towards the end of 19th and beginning of 20th century. They established that atoms are made of subatomic particles, electrons, protons, and neutrons, a concept very different from that of Dalton. Let us start. Please note down all the points are very important, and please note down and make your own notes. I welcome you once again. Discovery of subatomic particles. An insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles. That is, like charges repel each other and unlike charges attract each other. Discovery of electrons. In mid 1850s, many scientists, mainly Faraday, began to study electrical discharge in a partially evacuated tubes known as cathode ray discharge tubes. The figure on the screen shows a cathode ray discharge tube. This tube has a cathode negatively charged connected to a negative battery and anode connected to the positive side of a high voltage battery. The cathode ray tube is made of a glass containing two thin pieces of metal called electrodes sealed in it. These are electrodes. One is positive and negative, and this is a glass tube. The electrical discharge through the gases could be observed only at the low pressure and at very high voltages. The pressure of different gases could be adjusted by evacuation of glass tubes. So this is connected to vacuum pump which evacuates gases from the tubes. When sufficiently high voltage is applied across these electrodes, positive and negative, current starts flowing through the stream of particles moving in the tube from the negative electrode to the positive electrode. These were called cathode rays or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind anode with phosphorescent material zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot is developed on the coating. This figure with anode made holes and this material zinc sulfide coating, fluorescent coating, is shown in the figure. Discovery of subatomic particles. We will continue discussions. The results of these experiments discussed in the previous slide are summarized below. The cathode rays start from cathode and move towards the anode. These rays themselves are not visible, but their behavior can be observed with the help of certain kind of materials like fluorescent or phosphorescent, which glow when they hit them. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescence on the television screen coated with certain fluorescent or phosphorescent materials. In the absence of electrical or magnetic field, these travel in the straight line. In the presence of electrical or magnetic field, the behavior of cathode rays are similar to that of negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. So the characteristics of cathode rays, that is electrons, do not depend on the material of the electrodes. Please note, the material of electrode does not, the rays emitted does not depend on the material of the electrodes and the nature of the gas present in the cathode ray tube. So the electrons thus emitted are independent of the material of the electrodes as well as the nature of gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituents of all atoms. Charge to mass ratio. Charge to mass ratio of electron was determined by Thompson. For this, he subjected a beam of electrons released in the discharge tube as cathode rays under the influence of an electric and magnetic fields. So the electric field is produced by this positive and negative, and this N and S produces the magnetic field. This blue and yellow produces electric field, and this is a magnet and it produces the magnetic field. These were acting perpendicular to one another. Please see in the on the screen, the electric field is vertical and magnetic field are perpendicular to one another. These were acting perpendicular to one another as well as to the path followed by the electrons. See, this is a cathode and this is an anode, and the electrons pass through the magnetic field, electric and magnetic field. So these are perpendicular. So the magnetic field, electric field and path of the electrons are mutually perpendicular to one another. According to Thompson, the amount of deviation of particles from their path in the presence of electric and magnetic field depends on the following factors. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. So only when electric field is present, the electrons and go and hit the screen at the point A as shown in the figure. Similarly, when only magnetic field is applied, electrons strike the cathode ray tube at the point C. So point C is due to magnetic field, and point A, the path towards point A, is only due to electric field. By carefully balancing the electric and magnetic field strength, it is possible to bring back the electron to the path which is followed in the absence of electric or magnetic field, and they hit the screen at the point B. So, summarizing and recapitulating, the point B, the, the electrons hit at point B in the absence of electric and magnetic field. When we apply only electric field, it hits the screen at A, and when we apply only magnetic field, it hits the screen at the point C. Thompson argued that the amount of deviation of particles from their path in presence of electrical and magnetic field depends upon point number 1, the magnitude of the negative charge on the particle. Greater the magnitude of negative charge on the particle, greater is the interaction with the electric or magnetic field. Thus, greater is the deflection. So, here the negative charge on the particle also affects the path of electrons, the mass of the particle. So, the path also depends, the amount of deviation also depends on the mass of the particle. Lighter the particle, the greater is the deflection. Point number 3 is the strength of the electric or magnetic field. So, initially the first two were due to the particle, that is mass of particle and the charge of the particle. The point number 3 is due to electrical and magnetic field which is controlled externally. The deflection of electrons from its original path increases with the increase in voltage across the electrodes. So, deviation increases if we increase the voltage between these two plates, or strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by M, that is electric charge to mass of electron. Me is the mass of electron, E is the charge on the electron. So that E by M ratio value he found out to be 1.758820 into 10 to the power of 11 coulombs per kg. Let it be equation 1. Here Me is the mass of electron in kg and E is the magnitude of the charge on electron in coulomb. Since electrons are negatively charged, the charge on electron is minus E. Charge on the electron. R.A. Millikan, who lived between 1868 to 1953, devised a method known as oil drop experiment, that was in the year between 1906 to 1914, to determine the charge on the electrons. He found the charge on the electron to be minus 1.6 into 10 to the power of minus 19 coulombs. The present accepted value of electrical charge is minus 1.602176 into 10 to the power of minus 19 coulombs. The mass of electron, that represented by symbol m subscript e, was determined by combining these values. That is, E by m ratio, mass is represented by m into me subscript E is equal to charge divided by E divided by me, that is equal to 1.602176 into 10 to the power of minus 19 coulombs divided by 1.758820 into 10 to the power of 11 coulombs per kg. This denominator value is the value of E by me. Its value comes out to 9.1094 into 10 to the power of minus 31. Let it be 2.2. The details of the Millikan oil drop method are also shown in on your screen. In this method, Millikan oil drop method, oil droplets in the form of mist produced by the atomizer were allowed to enter through a tiny hole in the upper plate of the electrical condenser. So the diagram on the screen shows the Millikan oil drop apparatus for measuring charge E. In chamber, the forces acting on the oil drop are gravitational force, electrostatic force due to electric field, and a viscous drag force when oil drop is moving. Various parts of this figure are also shown. So this is a charge plate, positively charged, and oil droplets. This is the up here, it contains the oil droplets. This is atomizer. This is an atomizer and telescope through which we observe the dropping of oil. So here it is a small hole. This is a small hole and X-ray from the source appears here in between these two. And oil droplet under observation. This is the oil droplet under observation. And this is a charge plate. So this is a positively charged plate and this is a negatively charged plate. So we will describe once again. In Millikan oil drops method, oil droplets in the form of mist produced by atomizer were allowed to enter through a tiny hole in the upper plate of the electrical condenser. This is the electrical condenser. The downward motion of these droplets were viewed through the telescope. So there is a downward movement of oils equipped with a micrometer eyepiece. By measuring the rate of fall of these droplets, Millikan was able to measure the mass of oil droplets. The air inside the chamber was ionized by passing a beam of X-rays through it. The electrical charge on these oil droplets was acquired by collisions with gaseous ions. The fall of these charged oil droplets can be retarded, accelerated, or even made stationary, depending upon the charge on the droplets and polarity and strength of the voltage applied to the plate. By carefully measuring the effects of electrical field strength on the motion of oil droplets, Millikan concluded that The magnitude of electric charge represented by symbol Q, small q, on the droplet is always an integral multiple of electrical charge E. That is, Q is equal to Ne. Q is equal to Ne, where N is equal to 1, 2 or 3. Anything. An integer, whole integer. Discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of canal rays carrying positively charged particles. The characteristics of these positively charged particles are given below. The mass of positively charged particle depends on the nature of gas present in the cathode tube. These are simply the positively charged gaseous ions. The charge to mass ratio of particles depends on the gas from which these originate. Some of the positively charged particles carry a multiple of fundamental unit of electrical charge. The behavior of these particles in magnetic or electric field is exactly opposite to that observed for electron or cathode ray tube. The smallest and lightest positive ion was obtained from hydrogen, and the positive ion was called proton. These particles, protons and neutrons, were discovered by Chadwick in the year 1932 by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons were emitted. So, when he bombarded the thin sheet of beryllium by alpha particles, then some particles which were electrically neutral were also emitted, and he named these neutral particles as neutrons. So the table 1 shows the properties of fundamental particles. The fundamental particles are electron, proton and neutron. Electron is represented by symbol E and proton by symbol P, letter P, and neutron by N, all in small letters, and their absolute charge per coulomb is also shown on the screen. Electrons are negatively charged, hence this symbol is minus, and protons are positively charged, it is plus, and neutrons is electrically neutral, and hence its charge is 0. Relative charge. The relative charge of electron is -1 and proton is +1 and neutron is 0, and their mass per kg is electron is the lightest of all and its value is 9.109382 into 10 to the power of -31, whereas proton and neutron are the mass per kg of proton and neutron is equal, and it is of the order of 1.6726216 into 10 to the power of -27, which is same as neutron also. Mass per U is 0.00054 in the case of electron and 1.00727 in the case of proton, and neutron has mass per U as 1.00867, and the approximate mass per U is 0, 1 and 1 respectively for electron, proton and neutron. Atomic models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. The major problems before the scientists after the discovery of subatomic particles were to account for the stability of atom. So they have to account for the stability of atom and give reasons for it, and to compare the behavior of elements in terms of both physical and chemical properties. So they had to explain the behavior of elements and then to explain the formation of different kinds of molecules by combination of different atoms, and to understand the origin and nature of characteristics of electromagnetic radiation absorbed or emitted by atoms. So keeping in view this, different atomic models were proposed to explain distributions of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, two of these models, one proposed by J. Thompson and the other proposed by Ernst Rutherford, are discussed in these sections. First, let us take up Thomson model of atom. J. Thompson in the year 1898 proposed that an atom possesses a spherical shape, radius approximately 10 to the power of minus 10 meters, in which the positive charge is uniformly distributed. Hence, in Thomson's model, the positive charge is uniformly distributed in the spherical shape of radius approximately 10 to the power of minus 10 meters. And he said these electrons are embedded in such a manner as to give most stable electrostatic arrangement. So he showed these are the electrons and these are the positively charged sphere. Many different names are given to this model. For example, it is called plum pudding, raisin pudding, or watermelon, or positive charge with plums or seeds, or watermelon of positive charge with plums or seeds, electrons embedded into it. An important feature of this model is that the mass of atom is assumed to be uniformly distributed over atom. Although this model was able to explain the overall neutrality of atom, but was not consistent with the results of later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. Please note down important points. Next model is Rutherford's neutral Rutherford's nuclear model atom. Rutherford and his student Hans Geiger and Ernst Marsden bombarded very thin gold foil with alpha particles. So here please see the Rutherford's scattering experiment set up for Rutherford scattering equipment. So here there is a source of alpha particles and the alpha rays pass through the lead plate. He kept lead plate and a photographic plate. A stream of high energy alpha particles from a radioactive source was directed at a thin foil thickness approximately, this is the gold foil, approximately 100 nanometers. This is a very thin gold foil of the gold model. This ray alpha particles radioactive source fall on this. The thin gold foil had a circular fluorescent zinc sulfide. So this is a fluorescent zinc sulfide. The thin gold foil is circular around it. Whenever an alpha particle struck the screen, struck the screen, a tiny flash of light was produced at this point. So whenever the alpha particles passing through the gold foil struck it, and it is marked here. A light was produced. The results of this scattering experiment were quite unexpected. According to Thompson model of atom, the mass of each gold atom in the foil should have been spread evenly over the entire atom, and alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that particles will slow down and change the direction only by a small angle as they pass through the foil. It was observed that most of the alpha particles pass through the gold foil undeflected. So, this alpha particle passed through the gold foil and it remained undeflected. And the second point observed was a small fraction of alpha particles was deflected by a small angle. So, a small fraction of alpha particle was deflected by small angles. And the third point was a very few alpha particles, approximately 1 in 20,000, bounced back, that is, that were reflected by nearly 180 degrees. On this basis of observation, Rutherford drew the following conclusions regarding structure of atom. The first conclusion was most of the space in the atom is empty. He said the most of the atom is empty as most of the alpha particles pass through the foil undeflected. Next one, a few positively charged alpha particles were deflected. The deflection must be due to enormous repulsive force, showing that the positive charge of the atom is not spread throughout the atom as Thompson had presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. So, in the central part, so he said the positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. And the next point is calculation by Rutherford showed that the volume occupied by nucleus is negligibly small as compared to the total volume of the atom. The radius of atom is about 10 to the power of minus 10 meters, while that of nucleus is 10 to the power of minus 15. So 10 to the power minus 15 is smaller than 10 to the power of minus 10. One can appreciate the difference in size by realizing that if cricket ball represent a nucleus, then radius of atom would be about 5 kilometers. So if the radius of atom is 5 kilometers, then the size of the nucleus will be about the size of a cricket ball. So nucleus is very small. On the basis of these observations and conclusions, Rutherford proposed the nuclear model of atom. Hence, according to this model, the positive charge of most of the mass of atom was densely concentrated in small region, and this very small portion of atom was called nucleus. Please underline nucleus by Rutherford. The nucleus is surrounded by electrons that move around the nucleus. Electrons. So this nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular path called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and electrons that of the planets. The final observation was electrons and nucleus are held together by electrostatic forces of attraction. He also made that observation that electrons and nucleus are held together by electrostatic forces. Atomic number and mass number. The presence of positive charge on nucleus is due to protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to the atomic number. So number of protons equal to is the atomic number. For example, the number of protons in hydrogen is nucleus is 1, and in sodium atom it is 11. So number of protons, and therefore their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in the atom is equal to the number of protons, that is atomic number. For example, number of electrons in hydrogen is 1 and sodium is 11. The positive charge of nucleus is due to protons. The mass of nucleus is due to protons and neutrons. Protons and neutrons present in nucleus are collectively known as nucleons. That is, both protons and neutrons which are present in the nucleus are called nucleons. So atomic number Z is equal to number of protons in the nucleus of an atom that is equal to the number of electrons in the neutral atom. Let it be equation 3. While the positively charged nucleus is due to protons, the mass of nucleus due to protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as the mass number, and it is represented by the symbol capital A of the atom. Mass number A is equal to number of protons Z plus number of neutrons small n. Let it be equation 4. So you have to know what is atomic number, that is the number of protons in the nucleus of atom. And what is the mass number? A is equal to number of protons Z plus number of neutrons. Next we will take up isobars and isotopes. The composition of any atom can be represented by using the normal element symbol X with super subscript on the left hand side. So if A is the atomic mass number and Z is the atomic number, then any atom can be represented as AXZ. Here X is the symbol of element. X represents the element. A is the atomic mass number and Z is the atomic number. So A is atomic mass number and Z is the atomic number. Now we will take up isobars. Isobars are the atoms with same mass number but different atomic number. For example, 14C6 and 14N7. So both carbon and nitrogen are isobars having same atomic mass number, that is 14, but different atomic number. 6 in the case of carbon and 7 in the case of nitrogen. On the other hand, atoms with identical atomic number, that is Z is same but different A atomic mass number, are known as isotopes. Thus, isotopes will have the same atomic number but different atomic mass. Since mass number A equals number of protons plus number of neutrons, the difference between isotopes is due to the presence of different number of neutrons present in the nucleus. So the difference between isotopes is due to presence of here, because it is due to presence of neutrons in the nucleus. For example, consider an hydrogen atom. 99.985% of hydrogen atoms contain only one proton. This isotope is called protium. That is, atomic mass number is 1, atomic number is 1, and it is written as 1H1. Rest of the percentage of hydrogen atoms contain two other isotopes. that is one proton and one neutron, is called deuteron. So it is called 2D1, that its presence is 0.015%, and the other one possessing one proton and two neutrons is called tritium, that is 1T3. Sorry, it is 3T1. The latter isotope is found in traces amounts in Earth. Other examples of commonly occurring isotopes are carbon atoms containing 6, 7 and 8 neutrons. That is 12C6, 13C6 and 14C6. Another example is chlorine. Chlorine atoms contain 18 and 20 neutrons besides 17 protons. So it is 35Cl17 and 37Cl17. Lastly, an important point to note is isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all isotopes of a given element show same chemical behavior. Having studied about the Rutherford model, we will go through the drawbacks of a Rutherford model. An electron in the nuclear model describing planet-like orbit is under acceleration. According to electromagnetic theory of Maxwell, charged particles, when accelerated, should emit electromagnetic radiation. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from electronic motion. Thus, the orbit will continue to shrink because it is emitting radiations. Calculations show that it should take an electron only 10 to the power of minus 8 seconds to spiral into nucleus. But this is not happening. So, the Rutherford model does not satisfy the electromagnetic radiation part. Hence, Rutherford model cannot explain the stability of atom. If the motion of electron is described on the basis of classical mechanics and magnetic theory, since the motion of electrons in the orbit is leading to instability of atom, then why not consider electron as a stationary around nucleus? If the electrons were stationary, the electrostatic attraction between dense nucleus and electrons will pull the electrons toward the nucleus to form a miniature version of Thompson's model of an atom. Another serious setback of the Rutherford model is that it says nothing about the distribution of the electrons around the nucleus and energy of the electrons. Next, we will take up multiple choice questions. Question number 1. What was the value of charge to mass ratio, that is E by M ratio of electron as determined by J.J. Thompson? 4 options are given. You go through them very carefully. All of them are mentioned as charge per gram or charge per kg. So you have to remember the value of E to charge to mass ratio, and and recall and mark the correct answer. The correct charge to mass ratio is minus 1.76 into 10 to the power of 8 coulombs per gram. Next question. The number of electrons will together weigh 1 gram is. Four values are given and you have to mark the correct answer. First, let us analyze. Mass of an electron is equal to, you have to remember, 9.1096 into 10 to the power of minus 31 kg. And 1 gram or 10 to the power minus 3 kg is equal to 1 divided by 9.1096 into 10 to the power of minus 31. That simplifying, the value is 1.098 into 10 to the power of 27 electrons. This value is given as option A. Please mark it. Question number 3. How many electrons are present in a particle which carries a charge of 5.5 into 10 to the power of minus 16 coulomb? Four options are given. Please go through it. Let us analyze. So charge carried by one electron, we know that it is 1.6022 into 10 to the power of minus 19 coulombs. You have to remember this value. So electrons present in 5.5 into 10 to the power of minus 16 coulomb is 5.5 into 10 to the power of minus 16 divided by 1.6022 into 10 to the power of minus 19. So the value is 3432. Please mark it. Option A is the correct answer. Which experiment is responsible for finding out the charge of an electron? So four options are given. Silicon oil drop experiment, cathode ray discharge tube experiment, Rutherford X-ray scattering equipment, and photoelectric experiment. You have to remember and mark the correct answer. So silicon oil drop experiment is responsible for finding the charge of an electron. Next question. Which of the following statements about Thompson model of an atom are correct? An atom possesses an elliptical shape. So please read all the four and analyze. So and we have to remember that mass of atom is uniformly distributed over the atom. This was the Thompson model. He said that mass of atom is uniformly distributed. Which of the following conclusions regarding structure of atom is based on Rutherford's alpha particle scattering experiment? So you have to remember the conclusions. The positive charge is concentrated in a very small volume of atom. Second, the positive charge is scattered with electrons throughout the atom. This is wrong. The volume occupied by nucleus is half the volume of atom. That is wrong. Most of the space in an atom is occupied by neutron. This is also wrong. Only A is correct. Please mark it. Which of the following observations were not correct during Rutherford scattering experiment? Which is not correct. Most of the alpha particles pass through the gold foil undeflected. This is correct. A small fraction of alpha particles was deflected by small particles. This is also correct. A large number of alpha particles bounced back. A few of the particles. This is also correct. Only large number of particles were bounced back. So you have to remember. Answer C is the correct answer. Which is not correct. So answer C. So large number of alpha particles were bounced back is wrong actually. Only few were reflected. How many neutrons are there in 88 SR38? So four options are there: 38, 50, 126 and 88. So in 88 SR38, atomic number is equal to number of protons. So here number of protons is equal to 38. So number of neutrons will be 88 minus 38, that is equal to 50. So option B is the correct answer. Please mark it. Next question. An element with mass number 81 contains 31.7% more neutrons as compared to protons. Find the symbol of the atom. You are given four options. Option A 81 Se 34. Option B 81 Br 35. Option C 81 Kr 36. Option D 81 Rb 37. You have to analyze and mark the answer correctly. So therefore, mass number of the element is 81. It is given. That is, proton plus neutron is equal to 81. So let the number of protons be x. Therefore, x plus 31 divided by 100, because 31% more neutrons. So x plus 31.7 by 100 is equal to 1.317 x. Therefore, the value of x is equal to 34.958, approximately 35. So it is, the symbol of the element is Br. So Br, please mark the correct answer. Which of the following species is isoelectronic with CO? Four options are given. We have to analyze and mark the correct answer. Isoelectronic species means species having same number of electrons. In CO, the number of electrons is equal to 6 plus 8, that is equal to 14. In nitrogen, N2, number of electrons is equal to 7 plus 7, 14. So therefore, option B is the correct answer. Please mark it. Next question. In which of the following pairs the two species are both isoelectronic and isotopic? Atomic number C is equal to 20, AR is equal to 18, K is equal to 19, Mg is equal to 12, Fe is equal to 26 and Na is equal to 11. So these combinations are given. Pairs are given here. You have to analyze and mark it correctly. 39K plus and 40K plus contain same number of electrons. So they are isoelectronic. They have same atomic number but different mass number. So they are also isotopes. So you mark option B as the correct answer. Match the values of column 2 with column 1 and mark the appropriate choice. A table is given. Column 1 is serial number of column 1 is small a, small b, small c, small d. And here mass of electron, mass of proton, charge of electron, E by m of electron are the parameters given. In column 2, values are given for this at random, and its options are Roman 1, small 2, serial 1, 1, I, and IV. These are the options for column 2. You have to match which one is correct. Match column 1 with column 2. So options are given, various options. So you have to remember the values and mark the correct answer. B is correct. That is A is matched to 3. That is mass of electron is 9.1 into 10 to the power minus 31. B is mass of proton is equal to 1.67 into 10 to the power of minus 27. Charge of electron is 9.1 into 10 to the power of charge of electron is 1.7, charge of electrons is minus 1.602 into 10 to the power of minus 19, and E by M of electron is 1.76 into 10 to the power of 8 coulombs per gram. So you match here. A is to 3, B is to 1, C is to 2, and D is to 4. With this, we come to the end of sections 2.2 and 2.1. In the next lecture, we will discuss about developments leading to the Bohr's model of atom and Bohr's model for hydrogen atom. Till then, goodbye.